Right here we see one of the earliest surviving copies of Euclid's Elements. That's a document that Euclid used to define Euclidean geometry. It turns out that a lot of the words in Euclidean geometry are impossible to define precisely, but we're going to look at them in order to answer the question, what are the basic tools of Euclidean geometry?
What we call Euclidean geometry is credited to a mathematician named Euclid, who lived in Alexandria around 330 BCE. He created a comprehensive study of geometry based on deductive reasoning by using postulates, definitions, and theorems. Deductive reasoning is a type of logical reasoning that starts with assumptions and then uses logical implications and other rules to derive conclusions. In fact, Euclid was able to derive all of his theory by using only 5 postulates. Postulate is a special word. We could use the word axiom for it, but the word postulate's more common in geometry. A postulate is a mathematical statement that is just taken as true. It's not proven or anything like that. We just take a postulate and regard it as a fact. We'll see some postulates later. A definition is a formal statement that declares the meaning of a word, and sometimes a group of words or a phrase. Then we have theorems. Theorems are conditional statements that contain a hypothesis along with a conclusion. Let's take a closer look. So, the difference between a theorem and a postulate is that theorems are proven. They are proven by using definitions, using postulates, and possibly even using other theorems. In Euclidean geometry, we also often use figures and diagrams. Those figures and diagrams can be constructed with the use of just a straight edge and a compass. Those two special tools date all the way back to the time of Euclid. A straight edge is exactly like a ruler, but without any measurements on it. We use it for drawing straight lines. A compass is used for making circles or arcs. In this course, we're going to be using tools very similar to these.
There are some concepts in Euclidean geometry that are considered undefinable but are used to define other foundational objects. The reason that these objects are considered undefinable is because in mathematics, we need definitions that are precise and clear, and we also need a starting point. These are the starting points for Euclidean geometry. Point is one of these objects. We think of points as a location in space. We say that they have 0 or no dimensions, and the way that we represent them is with a single capital letter like P. Now, the reason that this is undefined is because, we said it's a location, so you might, for example, try to put it on the coordinate plane, but the coordinate plane itself, you'll notice, has lines involved in its definition, so that's not going to work. We don't want our undefined notions to really rely on each other. The next undefined notion is the notion of a line. We think of lines as a series of points extending infinitely in 2 directions. We think of them as being straight so that we're not accidentally describing a circle. But on the other hand, these are undefined, so we have to take our intuition. The way to represent or denote a line typically is with a lowercase letter like this, like M, or you could take 2 points on the line and give them names. And then what you would do is write their notation by writing PQ, and then above those points on the line, you make a little picture of a line to indicate the fact that this is a line. The next undefined notion that we have in Euclidean geometry is the concept of a plane. The way that we can describe a plane or think of a plane is as something consisting of infinitely many lines and that has a length and a width. Now we think of these as extending infinitely in their length and width direction. However, we don't give them any height whatsoever. They have zero height. So these are two-dimensional objects. And that contrasts with lines, which I said are one-dimensional objects. The way that we label or denote a plane is typically by using like a script or a uppercase italicized letter. Here I can call this guy P, but I'm going to call it R. Now, the characteristics of these undefined concepts are pretty important for us to nail down and understand. I said that points are zero-dimensional objects, which I'll abbreviate like that, and that they represent a location in space. We denote them with an uppercase letter like the P that's written right here. Next up, we said that lines consist of an infinite series of points, that they have one dimension, and that they can be represented by using a lowercase letter that's italicized like that M, or by taking points on the line that are named and writing something like PQ with a little line on top of it. Next up, we learned about planes. We learned to think of planes as things that consist of infinitely many lines in a length and width direction. And we said that they extend infinitely in those two dimensions. We also said that they have zero height. So these are two-dimensional objects with no height. And the way that we denote them or symbolize them is by using an uppercase italicized letter like that letter H. So to sum up, a point has no dimensions. We could think of it as a location on the coordinate plane, and when we do that, we designate it by an ordered pair, x, y, where x gives the horizontal position and y gives the vertical position. And we said that we identify them with single capital letters, such as P, sometimes Q, and so on. Lines consist of one-dimensional sets of infinite points. They have no beginning or end, and we identify them with a lowercase italicized letter or two capital letters representing 2 points on the line. And remember, when you do that, you put a little picture of a line up on top of them. Finally, we learned about planes and said that they're a two-dimensional set of all points extending in a length and width direction. And really, we can think of these as being flat, level surfaces with no height, no beginning or end, and we identify them by using a capital italicized letter. Another important concept in Euclidean geometry is distance. Let's analyze its meaning. And specifically, let's see if we can try to maybe define distance along a line between 2 points. We can't define distance or length of the entire line because we already said that lines are infinitely long. The distance between 2 points, however, that seems like it might be straightforward to define, perhaps by using a number line. Here I've placed that line segment above the number line, and then if I try to measure the distance, I would say, oh, the distance between those 2 points is 8. Well, that seems like a great idea, but if I were to change this number line like that, then you'll notice that, hey, all of a sudden the distance changed. And it changed just simply because I changed the number line. So if we were to back up a little bit and say, okay, let's define distance by using a number line, but on that number line, we need to use the concept of distance again. You can see that suddenly we're using circular logic. That means this is a very difficult concept to define. In fact, it's impossible. It's another undefined notion in Euclidean geometry. In this lesson, we've been trying to understand the basic building blocks of Euclidean geometry. And so far, we've taken some of the basic, primitive, undefined notions and described them. The cool thing in geometry is that you can put all those things together to make some really beautiful or complex shapes. What we're going to do next is we're going to look at some of the most important postulates that we use to understand these concepts better. Our first and possibly most important postulate that we'll learn about is the point existence postulate. Now, we already said that lines contain infinitely many points. That fact is derivable from this more primitive basic postulate, which says that a line contains at least 2 points. So if you take a look at this line right here, the postulate is telling me that I can always identify 2 points on the line. And I could call them A and B. And we could use those to refer to the line. I could say, okay, well, here's line AB by using that special notation. Or, as I already said, we can also use that italicized lowercase m or other such letters to represent the line. There's another important word to know here, and it's the word collinear. 2 points, or any number of points really, that are on the same line are called collinear points. There's another postulate that's kind of related, it's the converse almost, and it's called the unique line postulate. This postulate says that through any 2 points, there exists one and only one line. So right here on the screen, I see 2 points. I see point X and point Y. This postulate is telling me that I am guaranteed to be able to draw a line through those 2 points. Those points are collinear, which means actually that any 2 points are collinear once you draw the unique line between them. Let's check out some postulates for planes. Here we're going to look at the point existence postulate. This postulate tells me that a plane contains at least 3 non-collinear points. And take a look at that word non-collinear. What it means is that the objects are not all in a straight line. So what this postulate is telling me is that on any plane, I can draw 3 points, kind of like the guys I just drew right here, and they're non-collinear because it's pretty obvious, I think, that there's no straight line that's going to go through these 3 points, so they're non-collinear. Objects that are on the same plane, like those 3 points, are called coplanar. You can contrast the concept of coplanar with non-coplanar. An object would be non-coplanar if it were not on that plane. So for example, think of if I drew a point up above this plane. Remember that planes have no height, so that's always going to be possible. Then the point P is non-coplanar with points A, B, and C. Let's check out another postulate. It's called the unique plane postulate, and it states that through any 3 non-collinear points, there exists one and only one plane. So the points down here, points A, B, and C, they're non-collinear because it's pretty clear there's no straight line that goes through them. And this postulate tells me there's exactly one, just one, no more, plane that goes through this. And if you think about it, that'll start to make sense too. And remember that planes extend infinitely in their length and width directions. The last postulate for planes I'd like to tell you about is called the flat plane postulate. This postulate tells us that if 2 points are in a plane, then the line that contains those 2 points is entirely in the plane. Let's back up a little bit and remember that given any 2 points, for example, W and X, I'm guaranteed to have a line through them by the postulate that says that. And so right here, I am also guaranteed to have a line through the points Y and W, for example. Another thing that you might be wondering is, well, are these lines escaping from the plane since lines extend infinitely in 2 directions? And the answer is no, because the lines are contained in the plane because planes extend infinitely in both of their dimensions. It's just that they have no height whatsoever. Let's talk about how some different geometric figures intersect. The first thing that can intersect are distinct lines. Now, when distinct lines intersect, they do so at exactly one point. If we draw a picture of it, it should make quite a lot of sense. There's one line, and here's another line intersecting it. And if you think about what we know about lines, the fact that they intersect at exactly one point, it seems necessary. If two lines never intersect, two distinct lines never intersect, like these two lines right here, they're called parallel lines. We think of them as extending infinitely, always with the same distance apart. The next two things that can intersect are two planes. And this is a little trickier to think about. So what I'd like you to do is imagine that you're in, for example, a room, and that you can see a wall that's intersecting the floor. If you look closely at that corner, you'll see that it forms a line. And that's precisely what we're saying right here. We're saying that if two distinct planes intersect, then their intersection forms a line. So here's a plane S, here's a plane R, and we can see that their intersection creates a line, and it's containing these points A, B, and C. Finally, we can have a line that is intersecting a plane. Now, when I say this, I don't really mean a line that is in a plane, because obviously all of the points in the line would also be contained in the plane, but rather I mean something like line M here intersecting the plane R. And you could think of it as you take a piece of paper and push a pencil or a marker through it, and you'll notice that it intersects that paper at exactly one point. Well, right here, we can see that same thing happening. Right there, right here at the point B.